Okay, example 3 here, we're going to solve an exponential equation by using logarithms. So we have an exponential equation here, 11 to the x equals 101. We want to know when do we actually get 101? For what exponent, what value of x produces 101? So 11 to what power gets us there? Well, what we're going to do is we're going to take the logarithm of both sides. Now, the reason we're going to take the logarithm of both sides is because, as we've seen before, when we have a base raised to some exponent, when we take the logarithm of that, there's a property that's called like the power rule of logarithms that allows us to kind of move things around and get this piece that we're trying to solve for down onto our main line here, right? The main level, not up above, gets us down there. And that is this power rule, right, where we say log of x to some power is equal to p times log of x. We can move that power to the front. This is one of the things where, like, I always have trouble with logarithms, and I think there's a few good reasons why. One is that we don't spend a lot of time working on how to do logarithms by hand, so we don't just get the kind of mental muscle memory of working through logarithms and seeing what they are. So, for example, when you do multiplication tables, one, you start to practice like how to multiply things by 5, 5, 10, 15, 20, 25, 30. You start to like get solutions to the problem. Multiply something by 5, you see what you start with, you do your operation of times 5, you get your answer, and you start to establish a pattern. We don't do logarithms by hand, so we don't really get that pattern established into our mind. Another issue is that with something like multiplication, you can make area models. You can do like 1 times 5 and make a rectangle, or 2 times 5 and make a larger rectangle. And you can kind of rearrange shapes, and you can have this mental image of what the math is actually doing with real world objects. Now, since exponentials are repeated multiplication, we run into trouble when we're drawing images of exponentials, right? Because if we want to say length times width and make an area, that's fine. If we want to multiply something twice, if we want to do length times width times height, we can make a volume, and that'll be 3 factors in a multiplication problem. But as soon as we have more than 3 factors, or if you're thinking about exponents, if we have like an exponent greater than 3, if we have something raised to the 4th power or the 5th power, we don't really have ways to draw that because we don't have 4 or 5 spatial dimensions to draw pictures in or to imagine representations in. So, like, if we can't do it in that direction, well, we certainly can't do the inverse operation of trying to take some quantity and break it down by some kind of like repeated division. So there are all these kind of like hurdles for us to kind of mentally understand what we're actually doing. So one of the ways that I personally deal with that is that if I'm trying to look at something like this and say like, why is that? I'm gonna have a pretty hard time saying why this is true, but I can just go through and put an example and show, at least to myself, and give myself some confidence that it does work. So for example, if I have log, implied here, base 10 of 10 squared, that should equal, based off this power rule, 2 log 10. We should be able to bring the 2 down in front. So let's just check that that works. Well, 10 squared is 100, and the log of 100 is 2, right? Because this part is just saying 10 to what power equals 100? Well, 10 to the second power. Log of 100 is 2. Okay, on the right side, we have log of 10 over here. Well, 10 to what power, just looking right here, anyways, 10 to what power equals 10? Well, that's 1. So log of 10 is 1. So we get 1 times 2 on the right side, and we get 2 on the left side, and they equal each other. All right, we can go through, do another example, make sure it works for other numbers. So what about 10 to the 6? Well, 10 to the 6th power is 1,000,000. So we should be able to say log of 1,000,000 is equal to 6 log 10. Bring that exponent into the front. Make it 6 log 10. Well, the logarithm of 1,000,000 is 6, so 10, right? The answer is asking this question, 10 to what power? 10 raised to what power equals 1,000,000? Well, that's kind of by definition what we just said right here. 10 to the 6th power is a million. So our answer to this is 6. On the left side, we get 6. On the right side, we get 6. So for me, that's kind of where I mentally tap out. I don't have a great intuition for logarithms personally. Um, Not sure how the other math teachers feel, if their intuition is much stronger than mine, or if they're just kind of going through the same, um, you know, look at the example, see the example work, trust the example, use the formula kind of methodology here. Um, I think it'd be great to get to the point where you're feeling more intuitive about these things, because that just allows you to work with them a lot faster and easier without always having to go back to like, let me check those rules and make sure I'm doing the rules the right way. But at this stage, we are going to be a little bit rule based. Okay. So our rule here is going to be that if we have 11 to the x equals 101, if we do a log on both sides, that allows us to bring the x down in front. X log 11 equals log of 101. And at this stage, we just have x times some coefficient. So we're going to divide both sides by log 11. That's going to cancel out these and give me what x is equal to. Okay, so at this stage, this is just where we're heading to our calculator. We're typing in log 101 over log 11. And what we are going to get when we do that, when we go through those steps, get log 101 over log 11, we're going to get to an answer of approximately 1.9247.